have noticed that so far we have been doing problems which are essentially two dimensional. In the sense that we have been looking at equilibrium conditions that f x is equal to 0, summation f y is equal to 0 and summation tau z is equal to 0. So, we have been talking about two force components x and y and one component of the torque, and that is in z direction or the torque about the z axis. Now, let us generalize this to 3 dimensions. In 3 dimensions, obviously, the conditions that summation f vector is equal to 0 becomes summation f x is equal to 0, summation f y is equal to 0 and summation f z is equal to 0. Similarly, the condition that summation tau vector is 0 implies that summation of all the torques along the x axis is 0, summation tau y is 0 and summation tau z is 0. Similarly, now that we are talking about 3 dimensional cases, the engineering elements also now we have to consider in view of 3 dimensionality and see that they can apply forces in all 3 directions. Thus, remember in 2 dimensions there was a hinge or a pin joint which was like this, and it was capable of applying a force in x and y direction. Sometimes they are given as reactionary force R x and R y. In 3 dimensions, a similar joint is called a ball and socket joint, which is nothing but a socket in which a ball fits and it can rotate in any directions. So, a ball and socket joint, let me just now show it just like this, is capable of giving force in x, y and z all 3 directions. Let me make it like this. Let us say this is the z direction. On a socket joint, it can provide a force in x direction, it can provide a force in y direction and it can provide a force in z direction. This is the 3 dimensional counterpart of the pin joint or hinge joint of 2 dimensions. Let us solve a problem using this concept. Suppose a person wants to lift a very heavy load, and what he does is digs a hole in the ground and puts a pole in it, a long pole, hangs the weight somewhere in the middle, let us say at a distance of L1, let the length of the pole be L, and then he applies forces horizontally by 2 ropes in 2 directions like this. What is the tension in these ropes? That is we want to know, and what are the reactions here in x, y and z directions, n x, n y and n z. So, let us first choose our axis x, y and z. We choose our axis in such a manner that the pole is over the y axis and is in the y z plane. X, y and z. Let the pole be the yz plane over the y axis, making an angle theta from the y axis. The load is at a distance L1 and let the weight be W. The ropes are in the xy plane and let them make each of them an angle of alpha from the y axis. They are in the xy plane. We want to find out the tension in the rope and the forces Nx, the force Ny and the force Nz. At this point, I am making all the forces towards the origin, but it does not matter. So, let us now consider the equations for equilibrium. Summation over f gives summation f x is equal to 0, summation f y is equal to 0 and summation f z is equal to 0. Let us consider forces in all three directions. So, let me make the picture again. X, y, z. This is how the pole looks. I am making it slightly tilted. There is a weight W acting downwards. This length is L1. This entire length is L2. There is normal reaction Nx, Ny and Nz, and there are these two tensions in xy plane making angle alpha from here. So, if I were to write the force, let me call this tension 1, let me call this tension 2. T1 vector is nothing but minus T sine alpha I minus T cosine of alpha j, because the tension T1 has component in negative x direction and negative y direction. Similarly, tension T2 is equal to T sine alpha I minus T cosine alpha j. So, these are the two forces arising from the tension. The weight acts in the vertical direction. So, summation f x is equal to 0 gives me minus T sine alpha plus T sine alpha plus n x is equal to 0, or this implies, this cancels, that n x, the normal reaction in x direction is 0. It does not really matter, actually this should have been negative here. Similarly, summation f y is equal to 0 implies that minus T cosine alpha minus T cosine alpha minus n y is equal to 0, or n y is equal to 2 T cosine of alpha with a minus sign. So, n y has a magnitude of 2 T cosine alpha, and the negative sign in front indicates that it is in the direction opposite to what has been shown in the figure here, going towards the origin. So, n y is actually 2 T cosine alpha j. The third condition, the summation f z is equal to 0 gives minus n z minus w is equal to 0, or n z is equal to minus w, again showing that n z is equal to w and in the direction opposite to what has been shown, and therefore, Nz is equal to W times K. So, what we have determined on this rod or on the pole that has been sort of put in a ball in a socket joint is that there is a force on this due to the ground, due to the hole on the ground, which is equal to 2t cosine of alpha. There is a normal reaction in the z direction which is equal to W. There is a force W pulling it down. There is no force in the x direction, and then there are these two tensions in the xy plane working at an angle alpha like this. This angle is given to be theta. Let us now take the condition summation tau is equal to 0. To calculate tau, let us take the origin to be at the origin of the xyz system O, so that this comes out to be L1 cosine of theta j plus L1 sine of theta k, that is when L1 is this distance. So, distance where W is acting is L1 cosine theta j plus L1 sine theta k, cross product of minus W k. The other forces are tension. So, that would be plus L cosine of theta j plus L1 L sine of theta k cross. Since the two forces are acting at the same point, I can write the torque for their summation, which would be equal to minus 2 t cosine of alpha j, and this should be equal to 0. This condition would determine the tension T. So, let us work this out. The first term is going to give me j cross k, which is I L1 cosine theta times W. So, first term gives me I minus L1 W cosine theta. The second term again k cross j is 0. So, k cross j is minus I. So, it gives me plus 2 T L cosine alpha sine theta. So, this gives me plus 2 T L cosine alpha sine theta. This is also in I direction, and this is equal to 0, and that gives me T is equal to L1 W cosine theta divided by 2 L cosine alpha sine of theta. Once T is calculated, you can calculate N y, which is equal to 2 T cosine of alpha in magnitude, which will come out to be L1 W cosine theta over L sine of theta, and that is your answer.